Hello everyone, welcome to the online course on manufacturing processes. I am Kishore Kumar, Assistant Professor in the Department of Mechanical Engineering, MLR Institute of Technology. So today we will discuss numerical based on allowances. Already we have studied in the previous lecture what is the meaning of allowances related to casting, and we have studied all the cases. So in that lecture we couldn't get sufficient time to discuss this numerical based on that. So today we'll take some numerical and we'll further try to clear whatever the concept that we have studied related to these allowances. So four numerical for today lecture I have taken. We'll try to solve those numerical, and through that numerical we'll try to emphasize the concept that we have already done in the previous lecture. So we'll start with the allowances. Allowances already I have discussed in the previous lecture. What is the meaning of this one? As we know, in casting, material will be in the form of liquid state. So when material solidify from liquid to solid state, when phase transformation will be there. So as we know, whenever there is change in the phase, always there will be shrinkage in the material, or there will be contraction in the dimension. So because of that, whatever the product that we are going to produce through the casting, so pattern or the replica of the casting that we use to create the cavity, in that what will be the provisions? So what will be the dimension of the pattern? That is nothing but the allowances. So through numerical we will try to find out how to calculate those allowances. So first numerical that we have taken here is actually a cast iron material casting. So what this numerical read is a gray cast iron block of this particular dimension 200 by 100 mm by 10 mm we have to cast in sand casting. So what we have to do, in this problem it has been given that there is 1% of shrinkage in the pattern. So what we have to calculate? We have to calculate the ratio of volume of the pattern to the castings. First of all, we have to find out if 1% of a shrinkage is there in the pattern, then what will be the dimension of the pattern? I mean, what will be the volume of the pattern? Once we got what will be the dimension now or the volume of the pattern, then casting dimension already it is there, because this volume is given. It is nothing but the volume of the casting. So once we get the pattern volume, then after that we have to find out the ratio. So if we are writing VC as the volume of the casting, and if we will write Bp as the volume of the pattern, so what we have to calculate here? We have to calculate the ratio of Vp upon Vc. Means what is the ratio of volume of pattern to the volume of casting. So what will be the volume of casting? Directly we can write simply, because all the dimension is given. It is 200 by 100 by 10, and it will be mm cube. Okay. But what will be the volume of the pattern? So here it has been given that 1% shrinkage is there in this casting. As this is a volumetric casting, means all the three dimension and ill mold, means length will be there, breadth will be there, and of course height or thickness will be there. So we'll have to calculate what is the dimensional changes over there because of this shrinkage in all the three dimensions. So what will be the length? This shrinkage is 1%. So in this one, shrinkage is 1%. In this one also, in this breadth, shrinkage is 1%. And this thickness or the height, here also the shrinkage is 1%. So what we have to do when we are preparing the pattern, this extra dimension we need to provide over there in the pattern, so that whatever the cavity with the help of that pattern we are going to produce, that will have this extra dimension, so that after solidification, whatever the shrinkage is there, that can be easily compensated. Okay. So what will be the length? That is the change length after shrinkage. This will be simply 200, and 1% of shrinkage is there. 1% of shrinkage means if we are taking the 1%, so 1 upon 100, it will be 0.1. 0.01. So what will be the total dimension? I mean, what will be the change in this one? So it will be simply 200 into 1.01. Similarly, what will be the breadth? The second dimension, this will be simply, the value is, initial value is 100, so it will be 100 into 1.01. And the third dimension, thickness or the height, will be, we are taking h, so this is 10 given initial, so it will be 10 into 1.01. Now what will be the volume, final volume or the changed volume? That Vc VP will be simply 200 into 1.01 into 100 into 1.01 into this third dimension will be 10 into 1.01. This will be the volume of the pattern. So if we calculate this one, so VC is equal to volume of the casting is 200 by 100 by 10, and volume of the pattern that is changed after shrinkage, it is 200 into 100 into 10 into this cube of this one. This is once, twice and thrice. So it will be simply the cube of this one. So this will be into 1.01 whole cube. So what we have to calculate? We have to calculate the ratio, that is VP volume of the pattern upon volume of the casting. So this will be volume 200 by 100 by 10 divided by 200 by 100 by 10, and this is 1.01 whole cube. So this will be cancelled out, and finally it will be 1.01 whole cube. We will calculate this one. This will comes out to 1.03. So that will be the answer. So what is the meaning of this numerical? What we got from this numerical? Whenever we are designing a pattern, we know the meaning of the allowances. So this much of extra dimension in all the three, length, breadth and height or the thickness, we will have to provide, so that when there will be shrinkage or when there will be contraction during the phase transformation from liquid state to solid state during solidification of the casting. So this, if extra material or the extra dimension is provided to the pattern, will compensate whatever the shrinkage is happening during the casting solidification. We'll take the second example. This is also based on allowances, but slight difference is there. It is a hollow section. So generally there is a confusion among the students how to solve this kind of problems. So that is the reason we have taken this second numerical. But this is also based on the allowances, just to emphasize the concept of the allowance. Okay. So what the problem is, a gray cast iron block of size. This is the volume given 100 by 50 by 10 mm with a central spherical cavity of 4 mm, which is actually to be cast. Sand casting here is also there, but here the difference is casting, this volume of the casting is given, and inside there is a spherical cavity. Okay, na? And what is the diameter of that one? It is 4 meter. So the shrinkage allowance for the pattern is 3%. 3%. Here the allowance is given 3%. What we have to calculate? We have to calculate not a ratio. We have to calculate ratio of the volume of the pattern to the volume of the casting. Same thing here also we have to calculate VP upon VC. Okay, what will be the value of this one? So VC, first VC is very easy to calculate. What will be the volume of the casting? So we know this volume means this length is there, width is there, breadth is there, and this height is there. Okay, while a spherical cavity is inside. So we know the what will be the volume of the sphere. So we know it is nothing but 4 by 3 pi, and whatever the radius is there. So here diameter is given 4 meters. So it will be 2. So pi by 4 pi 2 cube. Okay, so that will be the volume of the casting. Okay, that is not an issue. The problem will come in the case of pattern, how to calculate that one. So once we'll get the volume of the pattern, after that we just have to find out the ratio of these two. So as we did in last numerical, similarly here we will do with a slight difference. What the difference will be, we will see here. So first, what will be the volume of the casting? It will be simply 100 into 50 into 10 minus, because spherical cavity is there. So that volume of that spherical cavity will be 4 upon 3. And what is the radius? It is 2. So this cube. So this is the volume of the casting. Now what will be the pattern? So for pattern, actually here 4 dimensions are there. That is the important thing we need to understand. Here length is there, then we have breadth is there, and height is there, and radius is also involved. But here radius will not increase. In fact, it will decrease. And by what dimension, by what amount it will decrease? It will decrease by the 3%. That is the only point that is different from the last numerical that we did in this numerical. So we'll have to be carefully. First, we'll have to find out when we are doing preparing or manufacturing this pattern. So in that, what will be the dimension? So changed length L prime. What will be the value? Initially, it is 100. So of course, it will be 100. And what will be the next value? I mean, what will be the changed value? The value will be 100 into, it is 3%. So 1.03. Similarly, what will be the breadth changed? That will be 50 into 1.03. Similarly, what will be the height or the thickness? That is h prime. This will be 10 into 1.03. And the fourth one, which is very, very important, which is different from the last numerical that we did, that is the r prime, changed radius. This will be, initially the radius was 2 and now it will decrease, it will not increase, and that value will be, as it is 3%, so it will be simply 0.97. So if we'll write the volume, we are writing on the second page. So changed volume, this pattern volume will be L prime into breadth into height. Okay, this 3 dimension will be there, minus what will be now the volume of the sphere, I mean the spherical cavity, pi. And now radius has changed, it is 0.97 and that cube. Okay, so this will be the volume of the pattern. What we have to calculate here? We have to, according to the problem, we have to simply calculate the ratio of these two. So this value we can put, just now we calculated in the problem what it was, 100 into 50 into 10, and as this 1.03 is coming in all the three, so simply we can take 1.03 cube, okay, minus this will be volume of the cavity, 4/3 pi, and r is nothing but 2 into 0.97. And what will be the denominator? This will be the volume of the casting. So what will be the volume of the casting? It is 100 into 50 into 10 minus 4/3 pi. Sorry. So and this will be pi and cube of 2. When we will calculate this one, finally we will get the value 1.09. So what was different in this numerical if we compare with the first numerical what we did? Here inside the casting there is a cavity. So it's very, very important to understand when we are calculating final dimension, that is the whatever after the shrinkage, what will be the dimension, whether it is length or breadth or height. In that, very carefully we'll have to find out the radius, because most of the students do actually mistake in this part only. So radius, generally they will put the expansion in radius, but this is not the case. You can imagine if a cylindrical block is there and inside there is a hollow section, so when there will be shrinkage, that radius will reduce. That is the important part only in this numerical, and because of that we have taken this numerical. Remaining all the things are same what we did in the last numerical. Okay, so we'll take again the third numerical just based on this concept only, and all these numericals are from the previous gate question. These numericals have not been taken randomly. All these numericals have been taken from the previous gate questions. So all these are standard questions. Okay, na? So just to make our concept what we have studied about the allowances in the pattern to make it more stronger. So okay, so what this third numerical is, cubic casting of side 50 mm. So here side length is given, and what is the shape? It is a cubical shape casting. Side is 50 mm, undergoes volumetric solidification, shrinkage, and volumetric solid contraction. What is the value? 4% and 6% respectively. So here the shrinkage, two shrinkages are given. One is 4% and another one is 6%. Okay, no riser is used here. Clearly it is mentioned that there is no riser in this casting. Assume uniform cooling throughout the section, I mean the part from where a phase transformation is occurring. It has been assumed that the heat dissipation is throughout same. Okay, so calculate what we have to calculate the side of the cube. So what we have to calculate, what will be the final dimension of the side of the cube of the casting after solidification. So this is a simple numerical, nothing is there. What we have to find out, first we'll have to find out, this is a cubical shape, so we know what will be the volume. Volume will be simply cube of this one. So what will be the volume? Initial volume, if we are writing Vi, so it will be simply what? Cube of this one, because we know the volume of a cube is nothing but the cube of the side length. So here side length is given 50 mm, so simply it will be 50 cube. But what will be the final volume after this solidification or after this shrinkage? So that value will be, of course this will be, but it will be reduced by, what is that value from which it will be reduced? 4%. So 4% means 0.96, and then second one is 6%, means 0.94. That is the two reduction. I mean, that is the two contraction in the dimension, or you can tell that is the two shrinkages which has been given in this numerical. And if we write the final side length as A prime, so what will be the volume? So A prime cube. If the final side length is A prime, so this will be the final volume of the cube after the shrinkage. Okay, so we have to find out in this problem what will be the value of A prime. A prime is equal to what? So easily we can calculate this one. What will be the value of A cube? Simply we'll take cube root from both sides, and then we can find out the value of A prime. So how we will do? Just see here. What will be A prime? A prime will be simply this 50 cube into 0.94, so into 0.96 and 1/3 of this. Okay, this is a lengthy calculation, but in engineering we can use calculator, so that is not a problem. Once you will calculate this one, the final value will comes out as this value. I have written the answer, it will comes out 48.32 mm. So what was the side length initially? Initial side length was 50 mm, and after these two shrinkages, after solidification, the final length or the final side length of the cube after solidification, it will become 48.32. So it was simple, nothing was there. It's a simple numerical, just further to emphasize the concept of the allowances. Now the last numerical that we have taken, this is also based on the allowances, but here both concepts have been involved. Means pattern allowances is there, as well as riser, whatever the compensation riser do, that is also given. So we have already studied these things, just numerical we have taken to further emphasize that concept. Okay, so what this numerical is, this is the last numerical that we'll take in this lecture. So while cooling a cubical casting, here also what is the shape of the casting? That is cubical shape, cubical casting. What is the side? Side is 40 mm and undergoes 3%, 4% and 5% of volume shrinkage. Three shrinkages that casting is going through: 3%, 4% and 5% during the liquid state, phase transition and solid state respectively. So in liquid state 3% shrinkage is there, in phase transformation 4% is there, and in solid state finally it is 5%. These three stages are there. What we have to calculate? We have to calculate the volume of the metal compensated by the riser. So what is the question? The question is how much volume this will be compensated by the riser. As you know, we have already studied or we have already discussed in the previous lecture, whenever there is phase transformation in the casting from the liquid state to solid state, actually pattern is taking care of the shrinkage as well as riser is also taking care of the shrinkage. If we will see this cooling curve which we have already studied, so it is temperature versus time, actually cooling curve. And if we will draw this one, so this graph looks like this. Okay, now this is the pouring temperature. If you remember, this is the pouring temperature when we are pouring the molten metal at this point, and when it reach at this point, then solidification start. Okay, now so here solidification is start, means phase transformation will start. For example, suppose we are pouring at 700 degrees centigrade and the metal start to solidify, for example, as 500 degrees centigrade. Okay, now so this temperature drop from 700 to 500, this will occur in this liquid state of the metal. When it will reach at this point, solidification will start. So solidification will start at this point and it will go up to this point. So at this point, all the liquid will be transformed into solid state. And finally, whatever the temperature is there in the solid state, it will reach to the room temperature or the furnace temperature or where we are doing the experiment. So this is the complete is the solid state part. So this is solid state section. This is phase transformation. We have already discussed all these things. Phase transformation, and this is the part where actually liquid metal is in completely liquid state. Here it is in solid plus liquid. Both states are there. So we have already studied that whenever there is solidification, means metal is transferring from liquid state to solid state, a starting position when the metal is in liquid state and when there is phase transformation. Up to this, whatever the compensation in the shrinkage is, it is taken care by the riser. Only up to this point. I have already stated this is taken care by the riser. And in solid state, this section, this is taken care by the pattern when the metal is in solid state. We have already studied this one during the solidification of the casting. So if you understand this one, after that there is nothing in this numerical. So what has been given in liquid state, the shrinkage is 3%. In phase transformation, it is 4%. And when the whole metal has been converted into solid, then the shrinkage is 5%. So this is being 5% is being taken care by the pattern, and this 3% and 4% is taken care by the riser. So what has been asked in this numerical? It has been asked calculate the volume of metal compensated by the riser. So as you know, riser can only take care when the metal is either in liquid state or it is in transition state. Transition state means it is transferring from liquid to solid, means some of the part of the metal is in solid state and some of the part of the metal is in liquid state. So only in these two stages, the compensation will be taken care by the riser of the shrinkage. Okay. So what will be the answer in this problem? 3% when the metal is in liquid state plus 4% when the metal is in transition phase. So totally it is 7%. So what is the volume which will be taken care by the riser? So this is the 7% of the volume, shrinkage volume, which will be taken care by the riser. So I hope this is clear to everyone. So we'll stop today's lecture here, and next lecture we will start some new topic and we'll discuss about that. For today, we are stopping this lecture at this point. Thank you.